Today's topic is some basics of complexity theory. Often when I teach, I realize that I need some tiny bit of complexity theory, even if the topic has nothing to do with complexity theory. So I need it either to motivate or to formalize things that otherwise would remain vague, or simply to put things into a bigger picture. So complexity theory is omnipresent, and it's also one of the scientific fields that has the most difficult open research questions, and that also keeps some of the greatest mysteries of the universe. So I would like to use it in my courses. I would assume a bit of knowledge about complexity theory from the students, but unfortunately sometimes it's simply not there. And that's not the fault of the students, it's simply not in the curriculum. So I said, okay, let's do something about it. Today's video is about the basics of complexity theory. Often we want the computer to solve some tasks for us. Today we'll have two running examples for such tasks. The first is the Google Maps search for shortest bike paths. The second is a hypothetical oracle for math students. I will abbreviate this by OFMS. The input to this oracle is a lemma that you have to prove for a homework assignment or to become a famous mathematician. The only thing that you still have to do, you have to code it in first-order logic. The output of the oracle is either no, it's false, the lemma is not true, or alternatively, it spits out a proof. A proof of the lemma. And that's a great thing. That's something we would like to have, such an OFMS. So one important question is, can the computer solve these tasks? For the first task, we have already seen it working in the background. So the answer is apparently yes. For the second problem, here our OFMS, this is really less clear. However, this is not the topic of today. We are today rather interested in the really important question. The really important question is, can the computer solve these tasks efficiently? What does that mean, efficiently? Is 1 millisecond of computation time good enough, or perhaps 1 second? How much should we give the computer? Well, you might say, oh, this depends on the type of task. And actually, what computer hardware are we talking about? And here the math students among us might say, see, here we leave science, this is all about engineering, but it's not quite true. There are some situations where we all agree that the computer is not efficient. For instance, if the computer takes more memory than the number of atoms on Earth. We all agree this is independent of the hardware. We can't store more atoms than we have atoms on the Earth, that's clear. Then there are also situations where we all agree that the computer is efficient. For this Google service example, for instance, the answer was rather quick. And you see, if we give him a harder task, like shortest bike route to Krakow, the time is still okay. I would really call this service efficient in practice. For the OFMS, at least Google is not running such a service. If you had such a thing, you could make this really a business model. Yeah, on the left side, you run your OFMS. On the right, you have some advertisements, and you will create a lot of traffic. Not only math students will use it, I bet. At the moment, no such system exists. So maybe there is some chance of a clear mathematical concept that comes close to model efficient computation. Our approach is to strip off all ugly things that are not essential, to cut down the idea of efficient computation to something mathematically robust, to simplify. The most important outcome of this approach is what is now known as polynomial-time computation. We look at problems that can be solved by a standard idealized computer in polynomial time. By this I mean that there should exist a computer program and a polynomial p of x, something like x squared or 2x to the 3, something like that, which polynomial depends on the problem. So that the program runs for at most p of x computation steps, where x is the size of the input. For the Google Maps program, the size would perhaps be the size of the map, so the number of cities plus streets. For the hypothetical oracle for math students, the situation is more difficult. Actually, it might be that the shortest proof of the lemma, which is the output, is incredibly long. So if the input size is just the number of symbols that you need to write down the lemma, this is probably not a good idea. And actually, are you really interested in a proof of your lemma whose proof takes 1 million pages or 1 billion pages? No. Actually, probably you are rather interested in a proof that precisely fits into the conference proceedings of your favorite conference, like 12 pages or 10 pages. So we modify the problem. The input is still the lemma, but also a number x. We are interested in a proof of the lemma of size at most x. Other proofs we don't care about. Such a modified OFMS is still a reasonably useful thing. And now it's perfectly, it makes sense to ask the question, is there an algorithm that solves the modified OFMS problem in polynomial time in the size of the lemma plus x, the size of the output proof? Now is the time to introduce our first complexity class, the class P. P is the class of all polynomial time solvable decision problems. So the answer should be either yes or no. There's an input and the output is either 0, 1, yes or no. In the beginning of video session 1 of my course Graph Homomorphisms and Universal Algebra, we have seen 3 examples of such decision problems: Lin-EQ, 3-colorability, and Horn-Sut. All of them were decision problems, and you might already know from other courses, or you will learn it in my course Universal Algebra, that Lin-EQ and Horn-Sut can be solved in polynomial time. For the 3-colorability problem, whether or not it belongs to the class P is an open research problem. Most people believe that there is no polynomial time algorithm for the 3-colorability problem, but unfortunately we don't know how to prove this. To explain why we don't believe that 3-colorability is in P, I need to introduce our second complexity class, the class NP. It's not true that NP stands for not polynomial. That would be far from the truth. NP stands for non-deterministic polynomial time. This class will contain all of P, and probably many more problems are in NP, but not in P. NP is the class of all decision problems where there exists a polynomial time algorithm that can verify for a given instance of a problem and its solution whether the solution is correct. So the running time must be bounded by a polynomial, p of n, where n is the size of the input instance. The algorithm is given both the instance of the problem and its solution, and has to verify that the solution is indeed a solution. To give you some examples, 3-colorability is in NP, I claim, because if we are given a graph and a 3-coloring of its vertices, we can decide in polynomial time whether the coloring is valid. That is, whether there is no 2 adjacent vertices that are colored with the same color. So this verification can be even done in linear time. We simply run over the set of all edges and verify the coloring condition. Our second example is the modified oracle for math students problem. I claim it is in NP. If we are given a lemma and this number x from the modification of our problem. And we are given a proof of size at most x. Then there exists a polynomial time algorithm that checks whether this is really a proof of the given lemma. To make this precise, I would have to tell you what actually a proof is precisely. There are different type of proof systems, but actually they are such that you can check them in polynomial time, usually. I will not go into the details of this. You have to attend a logic course to learn more about this. Okay, so that's 2 examples. Where does this name non-deterministic come from? Well, in reality, we can't expect that someone presents us the solution to our problem and we simply have to verify it. In reality, this is not enough. What we really want is that someone finds the solution for us. Of course, we could simply try all possible candidate solutions of size at most p of n and try them one by one. So this is what the non-deterministic stands for. You can imagine a computer which tries all of these candidate solutions in parallel to see whether one of them is correct. The algorithm then accepts if one of these parallel runs succeeds. So this is what non-deterministic stands for. Of course, we don't have such a parallel computer. So on the computers that we have nowadays on Earth, we would have to try solution candidate by solution candidate one after the other. If our solution candidates are simply strings of zeros and ones of some size m, then clearly there are 2 to the m possible solution candidates. So that's exponential. So if m grows, this function will quickly grow beyond every constant that you could imagine. Thanks to Corona, everybody knows what exponential growth can mean. It is something that you really want to avoid. This quickly exceeds all bounds that we can think of. Already for moderately small input sizes, the running time can be, longer than the lifetime of our universe. You don't want to wait for so long for your algorithm. And unfortunately, for some of the problems in NP, for example, for the 3-colorability problem, the best algorithms that we know have such an exponential running time. Of course, this could simply be because we are not clever enough. So to explain why we believe that 3-colorability is not in P, we need yet another complexity class. The class of NP-hard problems. To explain NP-hardness, I need the very important notion of a reduction. Suppose now that you have a decision problem A that you would like to solve. There's basically 2 ways of doing that. The first one is to sit down, think about an algorithm, prove that it's correct and efficient, then implement it, run it, and that's fine. But there's an alternative. The alternative is to look what you have in your toolbox, in your library. These are algorithms that others have implemented and tested and that you can use. So we assume that B is such a decision problem that you can solve in polynomial time by one of the algorithms in your toolbox. In some situations, it's possible to reduce A to B. Imagine it like some script that translates an input instance, little a, of your problem to an input instance of your program that solves B. To solve A, what you do is you first run the script on little a and then run the algorithm for B on the output of the script. For this approach to work, you need 2 properties. In order to obtain a polynomial time algorithm for A, you need to prove, 1, that little a has answer yes for problem A, if and only if the output of the reduction has answer yes for B. So these are 2 directions that you have to prove. It's if and only if. The second property that you also need is R itself can be computed in polynomial time. The resulting combined algorithm will again have polynomial running time. Now we are ready to define NPhard problems. A problem B, a decision problem B, is called NPhard if all problems in NP can be reduced in polynomial time to B. So the name NPhard is very easy to remember. A problem is NP-hard if it's at least as hard to solve as every problem in NP. How can we prove that a problem B is NP-hard? There are essentially 2 ways. The first way is to prove it by hand. The first problem that was shown to be NP-hard was the propositional satisfiability problem. This is often referred to as Cook's theorem. So here I will write by hand. And this is really some work. Luckily, Cook did it for the satisfiability problem. And I will not discuss how to do this in detail today. The second way is much more convenient. What you do there is you take a problem A that is already known to be NP-hard. And then you find a polynomial time reduction from A to B. And note that if you succeed in doing so, you will prove that B is NP-hard. The catch here is that polynomial time reductions, if you compose them, you will obtain again a polynomial time reduction. And in this way, you will, for instance, be able to prove that 3 colorability is NP-hard because you can reduce the propositional satisfiability problem to the 3 colorability problem. So there exists a polynomial time algorithm that takes a propositional formula and computes from this formula a graph such that the graph is 3 colorable if and only if this propositional formula is satisfiable. Note the following observation. This is really a consequence of what we've already seen. If 3 colorability is, or was, I should rather say was, in P, then P equals NP. Well, we already know P is a subset of NP, but if 3 colorability was in P, then every problem can be reduced to 3 colorability. That's what we know, because 3 colorability is NP-hard, and 3 colorability can then be solved in polynomial time, so every problem in NP can then be solved in polynomial time. And that's the reason why we don't believe that there is an efficient algorithm for 3 colorability. Because researchers have tried for many, many problems in NP to find polynomial time algorithms, and they have not succeeded. So basically all the efforts of humans in finding efficient algorithms for any problem in NP that failed, all the efforts that failed, they witnessed that 3 colorability is probably not in P. And that's the big open question, and many people believe that P is not equal to NP. If you solve this problem, you will get $1 million. It's one of the millennium's problems, one of the hardest problems of mathematics. So let's recap. What do we have? We got the class P. We've got the class NP, which contains P. We've got NPhard problems. And now comes our final complexity class for today. It's the intersection of NPhard and NP. That's called NP complete. Imagine NP complete problems as the hardest problems in NP. Of course, there are many more complexity classes. There's an entire complexity zoo. You can find a webpage called Complexity Zoo. And there's lots of classes. But the final thing I want to mention for today is that unless P equals NP, there are problems that are neither in P nor NP complete. And these problems are in NP. This is called Ladner's theorem. These are extremely artificial problems. There are problems in NP that are intermediate. They are neither in P nor NP complete. Unless P equals NP, which we don't think is true. Oops, unless P equals NP. Unfortunately, our sport program in Corona times is limited. Every day only yoga. A bit boring. I really miss my bouldering gym, but luckily we are still allowed to go out. Corona die erste. Alright.